So in this video, we'll be seeing about frequency division multiplexing. So frequency division multiplexing or FDM is a type of multiplexing method that is used to transfer data or to communicate from one point to another. So this method is actually a very efficient method when compared to other multiplexing methods like TDM and STDM, which stands for time division multiplexing and statistical time division multiplexing, where in those two methods they only allow the communication like only one message to be transferred at a time. But over here in this frequency division multiplexing, we can have n number of messages transferred from one place to another at a time. Now we can just communicate directly. Many channels can be used for communication, where in the other methods you can only have one channel where the communication has to be done. So this frequency division multiplexing is a technique where you have split the bandwidths or a set of huge bandwidth is given in which you divide the bandwidths for separate channels and then use them for communication. Like you can use a channel for data transfer, a channel for audio transfer, and then a channel for video transfer simultaneously in the same at the same time, which is not offered by the other multiplexing methods. So frequency division multiplexing is a technique by which the total bandwidth available in a communication medium is divided into a series of non-overlapping frequency bands, each of which is used to carry a separate signal. This allows a signal transmission medium such as a microwave, radio link, cable, or optical fiber to be shared multiple independent signals. Another use is to carry separate serial bits or segments of higher rate signal in parallel. So before we see more about frequency division multiplexing or FDM, let's know what multiplexing and demultiplexing is. So multiplexing is the process of combining multiple signals or combining multiple information into one single information. It is like having many data added up or summed up into one single data, and then it's getting transferred. The primary goal is to make efficient use of the available bandwidth. So in communication, while we have many too many data to be transferred, instead of using a wide range of bandwidth or frequency to just transfer one single data, we can just split that up into many channels and transfer multiple data. So that's why we use this multiplexing, where it helps us to transfer many data or multiple data. And deep multiplexing is like the reverse of multiplexing, where all the data that is summed up into one is split into the respective paths. That is, multiplexing can be used in the sender end, and then demultiplexing will be used in the receiver end. So, separate the data back and then give it properly to the respective channels. So, demultiplexing is the reverse process of multiplexing. It involves separating the combined signal back into the original individual signals at the receiver end. The demultiplexer is a device that performs this function. So this is what the FDM process looks like. Like you have the input lines given, and then it goes into the multiplexer, and then you have channels given for separate data to be sent out, and then you have the demultiplexer at the receiver end, and the data will get demultiplexed, and then you have the output lines. But before the demultiplexer, you also have filters where the data will be separated first, like all the multiplex signal will get separated into separate signals, and then later on they'll get demultiplexed before they are sent to the output lines. You can see that there are these channels given over here. These channels also have few gaps in between them called as the guard bands, so that we don't have the channels overlapping with each other, or so that we won't have any noise created at the output end or the receiver end. Just to prevent that noise and bandwidth overlapping, so that we don't lose any data or the data won't get overlapped with each other, we use these guard bands. Let's see about all these properties later, like what these guard bands are and what are these carrier frequencies that we use and what the bandwidth is. So over here you can see that I've shown the frequency division multiplexing with a set of arrows. The arrows at the beginning, they are the data that are coming into the multiplexer. And then once they come into the multiplexer, the data will get multiplexed and then it will get transferred to the demultiplexer end, where it will get filtered and then demultiplexed and sent to the receiver. So this is how the frequency division multiplexing works. And these are few key points that we need to know with respect to frequency division multiplexing. That is the carrier frequency, the carrier signals, and all the details regarding to the signals like message frequency, carrier frequency, and then the modulated frequencies. So each individual signal is modulated onto its own carrier frequency. The carrier frequencies are spaced apart so that their respective bandwidths do not overlap. So this carrier frequency is the one which will actually carry the message signal and or the message from one point to another, like from the source to destination, that is sender to receiver. And we have to make sure that these carrier frequencies are separated or spaced apart so that they don't overlap with each other and you won't have the noise created at the receiver end due to extra data or unwanted data present in it. And bandwidth. The total available bandwidth of the communication channel is divided into non-overlapping frequency bands, each allocated to a separate signal. So, like I said, instead of having 1 gigahertz or even much more data, frequency range used just for one separate data transfer, we can just split it up into multiple data channels like or multiple frequencies, subdivision of frequencies into like hertz, uh, then megahertz instead of using it just like 1 gigahertz alone. And then we'll just have that as separate bandwidths given to separate channels or separate uh, data transfer sets, like the way the radios work, the FM radios, where we have these things like 92.5 FM, 93.5 FM, and etc. Instead of using the whole range of frequency to just give it for one separate channel, we're just using it for different channels. Just like that, we can be using this bandwidth over here, where the data can be transferred efficiently, and we don't need to have specific priorities given for the data, like we have it in the time division multiplexing and then statistical time division multiplexing, where we need to prioritize the data first, or we'll only have a certain data transferred at one time, and then we'll have to wait for the less priority data to be transferred after the more priority data transferred. So that's not happening over here. We just have the data transferred simultaneously. And then guard bands. Some frequency gaps, there are small frequency gaps known as guard bands that are often placed between adjacent frequency bands to prevent the interference between signals, like I said before, so that we don't have the message overlapping with each other and creating noise at the receiver end. We use these guard bands. It's like a vacuum or a space present between two channels, like you don't use that particular bandwidth or that particular frequency to communicate anything between any sources. It's only after that frequency and below that frequency. Only those two players are used, and a certain set of frequency is not being used. And that's what these guard bands are. They just help us to prevent interference between signals. So now we'll see few applications of these frequency division multiplexing. So they are used in radio broadcasting, television broadcasting, telephone networks, cable televisions, and also in satellite communication. So let's see one by one about what these are. So radio broadcasting, each radio stations broadcast at a different frequency within the radio spectrum, allowing multiple stations to operate simultaneously without any interference. So you can have different stations operating at their own frequency and they won't be interfered with any other signal or any other noise coming from the outside. So that's why we use this frequency division multiplexing. And then for television broadcasting, analog TV channels are transmitted using different frequency bands. Each TV channel is assigned a specific frequency range. Then telephone networks, each telephone network, earlier network systems used FDM to carry multiple telephone calls over a single cable by assigning each call a different frequency. So here in this So here you can see in this image that's beside this that there are multiple cable lines running throughout the city. It'll just be too much hectic to have all these cables running. There is how we previously had before we found out about these multiplexing techniques. You had to have a separate cable running for a separate channel, or if you need to communicate from one person to multiple persons, you need to have those many multiple cable lines so that you can communicate with each other. You cannot have that done within the same cable line. But after finding all these multiplexing techniques, we have the advantages of, you know, not need, there's no need for having the cable lines running too much. Just you can just do the communications in the one single cable line. The data will just be multiplexed and be sent on the other side where it will get demultiplexed respectively to be sent to each and every receiver. And then cable televisions, multiple TV channels are transmitted over a single coaxial cable. So over here also we have the multiplexing operation okay, where the data, all the channels are multiplexed into a single channel, and then you have it, or They're just multiplexed and summed up together. And the receiver, they again get demultiplexed and then sent respectively to each cable televisions. And then you have it in satellite communications. So frequency division multiplexing is using satellite transmission, satellite systems to transmit multiple signals to and from satellites. So, these can be used in multiple ways like transferring data, transferring video, transferring audio. That's what we saw over here. Like you can transfer radio, that is audio, and then television broadcasting, video broadcasting, and data broadcasting, that is in satellite systems. So you can transfer multiple types of data that too in simultaneously without any delay of prioritization of data and all those things. So these are the applications of frequency division multiplexing. So let's see about few advantages of it. Advantages are efficient use of bandwidth, continuous transmission, and low latency. So efficient use of bandwidth, the bandwidth are like an example that I gave before. If you have 1 gigahertz of bandwidth given to transfer, communicate, a particular data, you don't need to use the whole bandwidth for just one communication because you won't be using the whole frequency for that. You'll just be using a certain set of frequency and the other rest will be just wasted. So instead of just wasting that, we'll just split up into different channels and then use that for transfer of data. And then continuous transmission, like I said, you don't need to prioritize a certain data or the data won't be sent like one per time. You can just send the data simultaneously at a time through the channels. They don't need to wait for a priority to be given and all those things. Low latency. Low latency is also just like, the previous point, continuous transmission, where you don't need to have any time delays between the transfer of messages like you have in the TDM and STDM processes. You can just transfer data continuously. There's no need for any delay to be there between the data. That's what the low latency also says over here. So that's it. Thank you.